In this section, we will solve some exponential equations and some logarithmic equations and look at some problems involving compound interest. Since the exponential function is 1-to-1, we know that whenever two exponentials are equal, if they have the same base, then the exponents must be equal. So, for example, an equation like 4 to the x plus 1 power equals 64 can be made more simple since we can express 64 as 4 to the third power. And so this becomes 4 to the x plus 1 power equals 4 to the third power. And now clearly x plus 1 must equal 3, and that gives us the solution x equals 2. And that's easily verified in the original equation. The next equation to solve is a similar situation. 3 to the 2x minus 8 equals 3 to the 5x plus 1. So since these exponentials have the same base, we know that the exponents must be equal. So 2x minus 8 must equal 5x plus 1. Solving for x, we will shift the 2x over here to give us 3x, and the 1 over there to give us, what is that, negative 9. And now negative 9 divided by 3 is negative 3. So x equals negative 3, and again, that can be easily verified in the original equation. What happens if the bases in the exponential are not the same? That's an important question, because if the bases are not the same, you can't use the 1-to-1 property. And so instead, what we do is take the logarithm of both sides. And since our calculator has a log base 10 key and a log base e key, we usually take the log either base 10 or base e. So if we look at 2 to the 1 minus x power equals 3, we see the bases are not the same, but if we take the base 10 logarithm of both sides of this equation, since the numbers are equal, their logarithms must be equal, so we have 2 to the 1 minus x and take the log of that. We have 3, take the log of that. Now, log of 3 is just a number, and on the left-hand side, we can use properties of logs to simplify that expression. And we would, the exponent 1 minus x will become a coefficient. So we have 1 minus x log 2 equals log 3. Now we can divide by log of 2. If we divide both sides by log of 2, we get 1 minus x equals log of 3 divided by log of 2. And now we just have to rearrange our terms so we can solve for x. And so when we do this, we will get x on the right-hand side equals 1 minus the log of 3 divided by the log of 2. So I will let you figure out what that value is on your calculator, rounded to 6 decimal places. We can also do graphical solutions. To do a graphical solution of an equation such as e to the 1 minus 4x equals 2, simply select the left-hand side to be one of the functions in your calculator. So say you let y1 equal e to the 1 minus 4x power, and let the right-hand side be the other function, say y2 is equal to 2. Then on your calculator, what you would do is calculate the intersection. So to access that, it's the second function of the trace key, which is calculate. The second function of the trace key is calculate, or calc. And you want to calculate intersection, because that's what you want. You want the intersection of these two graphs. The graph of e to the power 1 minus 4x intersected with the graph of y equals 2. You may have to do some window sizing, some resizing of your x-axis maybe, or your y-axis to get a good look at the intersection point. But you can find the intersection point graphically by doing this process. Now we also have this type of equation, and we'll solve these equations algebraically. The first one, let me make a little room because I know it's going to take some room to do it. In the first equation, there happens to be a typo on this problem. That should not be a 3. That should be e to the 2x. So I'm going to write the corrected equation here. It should be e to the 2x power minus 3e to the x power plus 2 is equal to 0. Now we should recognize this as quadratic in form. It's not a quadratic equation, but it is quadratic in form. The exponent here is double the exponent there, and here we have a constant. So we can actually factor this as a quadratic. We don't have to go through the whole substitution process. We know that we have to get e to the 2x and e to the x for the middle term. That means that the first two in the binomial must be e to the x and e to the x. We also have to have two minuses, and we have to have a 2 and a 1, so I guess this is the correct factorization. And it indeed does work out. If we check the middle term, we get negative 3 e to the x. So that tells us that e to the x minus 2 equals 0, or e to the x minus 1 equals 0. If e to the x minus 2 equals 0, then e to the x equals 2. And now we can take the natural log of both sides, since the exponential function we're using is a base e function. So the natural log of e to the x equals the natural log of 2. And of course, the natural log of e to the x is just x. And so we get the solution x equals the natural log of 2. On the other hand, we have e to the x power minus 1 equals 0, which gives us e to the x power equals 1. And we know that the exponent has to be 0 because e to the 0 is 1, so x equals 0. So there are our two solutions. X equals the log of 2, the natural log of 2, x equals 0. Okay, so now that leaves the next equation to solve, which is, let me make a little room here. The next equation is x squared to the 2x power minus x squared times 2 to the x power minus 2 to the x power equals 0. The first thing I notice there is the common factor of 2 to the x power. So I'm going to factor the left-hand side. That will give me 2 to the x as the common factor multiplied by x squared minus 1, and so that equals 0. And now we set each factor equal to 0, just like we've always done. So 2 to the x power equals 0, or x squared minus 1 equals 0. Well, we know that 2 to the x power equals 0 has no solution, because that exponential function, if we think and remember about the graph, it never actually crosses the x-axis. So there's no solution here. So the only solution comes from x squared minus 1 equals 0, and those solutions are x equals 1, x equals minus 1. And so we have two solutions, x equals 1 and x equals negative 1, for this second equation. Logarithmic equations are solved by using laws of logarithms. And so we see here on the left-hand side, where we have log of x plus the log of x minus 1, we have the sum of two logs. And from our laws of logarithms, the sum of two logs is the log of a product. And so therefore the left-hand side can be rewritten as the logarithm of x times x minus 1. That's the left-hand side, using law of logs. The right-hand side, we'll just leave it as the log of 4x. Because now we know that the logarithms of these two expressions, that expression and that expression, the logarithms of those two things are equal. Well, the logarithm function is also one-to-one, just like the exponential function. So if the logarithms are equal, then the two expressions must be equal. So x squared minus x, which is what I get on the left-hand side when I multiply that out, must equal 4x. So now this is just a quadratic equation. We get x squared minus 5x equals 0, which gives us, if we factor, x times x minus 5 equals 0. And so we get two solutions, x equals 0, x equals 5. We eliminate the solution x equals 0 because that substituted here and substituted here and substituted here gives invalid arguments for the log function. Remember, we cannot take the log of 0, we cannot take the log of negative 1, and again, we cannot take the log of 0. So x equals 0 is a discarded solution. The only solution is x equals 5. Our second logarithmic equation uses the natural log base. That's not an issue. We have the natural log of x is equal to 10. So what we'll do is rewrite that in exponential form. If the natural log of x is equal to 10, the base on that natural log function is e. 10 is the exponent, so we get e to the 10th power equals x. And that's the solution. Just remember that e is a number, so e to the 10th power is a number, and so you've got the number that's equal to x. That one was actually pretty easy. Well, this one's easy too. This is a base 10 log of 3x plus 5 equal to 2. So if we rewrite that in exponential form, we get the base 10 raised to the exponent 2 equals 3x plus 5. Now this is not even worth our time to solve on this note. I'm going to let you solve that equation for yourself. Don't be confused by 10 squared, it's just 100. So solve that one on your own. The next one, we have to get the term that contains the log by itself. Since there's a negative sign in the front of it, I'm going to ship it over to the right-hand side, and I'm going to bring that 3 over to the left-hand side. So when I rewrite this equation, I will have 4 minus 3, which is 1, is equal to the logarithm of 3 minus x. So again, I can express this in exponent form. Remember, this is a base 10 log, and 1 is the exponent. So that means 10 to the first power equals 3 minus x. Again, I'm pretty sure you can finish solving that one on your own. So I'll help you with the last one here, which I think is more challenging. This last one is, what is this last one? Here it is. The log base 2 of x plus the log base 2 of x minus 3 is equal to 2. Well, let's use properties of logs. Laws of logarithms tell us that the sum of two logs is the log of a product. And so we have the base 2 log of the product, x times x minus 3, and that has to equal 2. Once again, we can re-express this in exponent form, the base 2 log raised to the power 2 here. So the base 2 log, and this 2 is the exponent. And so we rewrite this as 2 squared equals x times x minus 3. 2 squared is 4, so 4 equals x squared minus 3x. That's a quadratic equation. I'll let you solve that one on your own. Remember, when you get to the solution, to verify that the values that you get for x are valid when replaced into the original equation. In other words, make sure you check the solutions, because sometimes you get additional solutions that aren't right for the original equation. To use a graphing device to find the solutions, you would simply proceed the same way as before. Simply graph the left-hand side, which is, let that be your y1 function. Your y1 function will be ln of x. That's the base e log of x, the natural log of x. And your y2 function will be the line 3 minus x. Graph those two functions, find the intersection point, and use second trace, which is calc, and calculate the intersection. So you can do that one on your own. It's really not something that we can do in voiceover notes. The only things left are application problems. I think I've selected that looks like there are 3 problems, but the last 2 are kind of the same. So I'll just get you started on these. Atmospheric pressure P in kilopascals at altitude h in kilometers is governed by this formula. The natural log of P divided by P sub 0 is equal to negative of h divided by k. We're given that k is 7 and P sub 0 is 100 are constants. We want to solve this equation for P. So to solve this equation for P, we will re-express it in exponent form, because we only have a logarithm on one side. So let's express this in exponent form. It tells us that e to the negative h over k is equal to p over p sub 0. We're solving for p, so we just have to multiply by p sub 0. And so we end up with p sub 0 times e to the power negative h over k is equal to p. So we've solved it for p. Now we're to use that part A, which has given us this equation solved for P, in order to find the pressure at an altitude of 4 kilometers. The altitude is the value of h. The value of k is given as 7, and the value of P sub 0 is given as 100. So this is just a matter of substituting that into the equation, substituting those constants into this formula or equation, and finding the value using your calculator. Okay, the next problem deals with compounding interest quarterly. Remember, the formula for compounding interest periodically is A of t is equal to P sub 0, or actually it's just P. I think we don't use P sub 0 here, we just use P, times 1 plus the interest rate divided by n, the number of compounding periods in a year, raised to the power n times t. So we're given that the person is investing $5,000, so that's the value of P, so A of t is equal to 5,000 times 1 plus R, the interest rate is 8.5%, which is 0.085 yearly interest rate, and we're compounding quarterly, and there are 4 quarters in a year, so that's divided by 4, to the power n times t. And again, n is 4, and we want to find the amount after 3 years, so t is 3. So n is 4, and t is 3, so 4 times 3 is 12. So you just have to enter this into your calculator to find the amount after 3 years. This is just like a problem we've done before, so I'm not going to work this one out all the way for you. You can do this one on your own. The next part, the B part, is something slightly different. We're asked how long it will take for the investment to double. We want to double the investment. Well, if we double the investment, it means that since we're starting with $5,000, we're going to end up with $10,000. So let's see how this one works. First, I'll make some room here. So now we've got to find, if we know that we're going to end up with a double, that means we know we're going to end up with $10,000, and that still equals our original amount, 5,000, just substituting into the formula, times 1 plus 0.085 divided by 4 to the power n times t, which is 4 times t. So now you can see the difference here is we have to solve for the t, which is in the exponent, and that's where the logarithm comes in. So first, let's divide both sides by 5,000, and that will give us 2 is equal to 1 plus 0.085 divided by 4 to the power 4 times t. Now we're going to rewrite this as a, I have to go over here, I think, rewrite this as a logarithm. In other words, what I'm going to do next is just, I'll use the natural logarithm because I like that the best. So I'll take the natural logarithm of both sides. So I'm going to end up with the natural logarithm of 2 is equal to, I'm going to have to write it under because I'm sort of out of space. Well, I think I can move it over a little bit. You can't see that. There you go. The natural logarithm of 2 is equal to the natural logarithm of what I have in parentheses, which is 1 plus 0.085 over 4 to the power and 4 times t. Now I can use laws of logarithms to simplify the right-hand side. I still have the natural logarithm of 2, but on the right-hand side, the 4t exponent becomes a coefficient, so I have 4t times the natural logarithm of 1 plus 0.085 over 4. Now, the natural log of 1 plus 0.085 over 4 is just a number. So I'm going to divide by that number, and when I do that, oh, and also, while I'm at it, I may as well divide by the 4 as well. It's all part of the number over there. So I have the natural log of 2 divided by 4 times the natural log of 1 plus 0.085 over 4 raised to no power, actually, is equal to t. And so that's it. Time is equal to that expression. So now it's just a matter of entering that expression correctly into your calculator. I guess it seems like I'm saying it's just a matter of doing that, but that can be kind of complicated to enter. Just give it a shot, see what you can do, and that's all there is to it. The last problem is similar. We want to find the time required for an investment of $5,000 to grow to $8,000 at the interest rate of 7.5% per year, compounded quarterly. So we have quarterly compounding, so our formula is A of t is equal to P times 1 plus R over n to the n times t. And now we want the investment of $5,000 has to grow to $8,000. So we want A of t to be 8,000. Our original investment was 5,000. Our interest rate is 7.5%, which is 0.075. It's compounded quarterly, so n is 4, and n times t is going to be 4t. So once again, we're solving for the variable which is in the exponent, and that's going to involve logarithms. And so I'll get you going here. We're going to divide both sides by 5,000. So on the left-hand side, we'll get 8 over 5. And on the right-hand side, we have 1 plus 0.075 over 4 raised to the power 4t. Now let me show you how you can simplify 1 plus 0.075 over 4. It's just a mixed number. So we multiply 4 times 1 and get 4. And we add that to the 0.075 and we divide by 4. Now you can take that and put it in your calculator if you want, but it's a little bit easier to enter into the function now. So over here I'm going to end up with 8 over 5 equals 4.075 divided by 4 to the power 4t. So I'm going to take the logarithm of both sides. I'm going to use the natural logarithm again. So the natural logarithm of 8 over 5 is equal to the natural logarithm of 4.075 divided by 4 to the power 4t. Now again, the 4t, since it's a power on something you're taking the log of, can become a coefficient. So we get the natural log of 8 divided by 5 is equal to 4t times the natural log of 4.075 divided by 4. Now I know it looks kind of like a mess, but it's not really that bad. We're solving for t, so the t is connected to this 4 and to this right here, just like before. So all we're going to do is divide by that. So we have the natural log of 8 over 5 divided by 4 times the natural log of 4.075 over 4, and that is equal to t. So it's just a matter again of entering that into the calculator and entering it carefully and correctly to get the proper value of t. You may want to simplify the numerator a little bit and write it as the natural log of 8 minus the natural log of 5, but I don't know if that's really more simple or not. It's just a question of how you prefer to enter expressions into the calculator. And you can enter it just like this, the natural log of 8 over 5, and then use your division symbol. But then if you do that, you have to make sure that you use grouping symbols down here to group these things together. So you divide by that product. At any rate, you should be able to figure out what the time is.